Hi there, and welcome to another episode of Physics with Graeme. In this episode, we will be solving three different types of problems. One forces problem, one energy problem, and one kinematics problem. All of our problems will be based off of the famous Looney Tunes cartoon Roadrunner and Wile E. Coyote. Let's take a look at the first clip we will be analyzing. In this clip, we see Wile E. Coyote chasing the Roadrunner at what appears to be the fastest he can run. Right off the bat, we have an issue with the physics in this cartoon, as the maximum speed of a coyote is twice as fast as that of a roadrunner in real life. However, it could be that Wile E. Coyote is not one of the faster coyotes on the planet, so therefore, for the purposes of this question, we will assume that he can only run as fast as the roadrunner can, which is 32 kilometers an hour or 8.9 meters per second. In this clip, in an attempt to lose him, the roadrunner leads the coyote up around an arc of an unknown height. The reason the two stay on this loop and don't fall off is due to something called centripetal force. Centripetal force can be defined as an inward force acting to constrain a rotating object to a circular path. More simply put, centripetal force is the force applied to the roadrunner and the coyote by the arc that keeps them moving in a circle. According to Newton's law, without this force, the coyote and roadrunner should continue to move in a straight line in the direction of their velocity. But since they are acted upon by an unbalanced force, they are accelerated towards the center of the circle and therefore continue in their circular motion. If we assume that the two are traveling at the minimum speed required to make it around the loop, and that their velocity was that of the roadrunner, which was 8.9 meters per second, we can calculate the height of the loop. The first step will be to draw a free body diagram. For simplicity, we will do our calculations assuming that they are both at the top of the arc. When this is the case, and they are traveling at the minimum speed required to make it around, the only force contributing to the centripetal force is the force of gravity. Therefore, the centripetal force will be equal to the force of gravity, which can be expressed as mass times acceleration due to gravity. The equation for centripetal force is mass times centripetal acceleration, which can also be written as mass times velocity squared over the radius. Subbing these variables into our original equation gives us mv squared over r is equal to mg. Now that we have our complete equation, we must simplify in order to solve for the radius r. In doing this, we are able to cancel out mass, and the equation becomes r is equal to v squared over g. We know that the velocity of the two is 8.9 meters per second and that acceleration due to gravity is 9.8 meters per second squared. We can now plug in our values and solve, which will give us an answer of 8.1 meters. Finally, we know that the height or diameter of the loop is equal to 2r, so we multiply the radius by 2, giving us an answer of 16 meters. Therefore, according to physics, the loop is 16 meters tall. In the clip, the roadrunner and the coyote are approximately the same size. If we assume that both the coyote and the roadrunner are around 1 meter tall, then this answer for the height of the loop makes sense, because when we compare it to the height of the roadrunner in this picture, it seems accurate. Therefore, this is an example of good physics within this cartoon. In the clip, however, they do not go all the way around the circle as Roadrunner stops the coyote at the top. At this point, since he is not moving, gravity takes over and he falls straight towards the ground. Using our knowledge of energy, we will now figure out how fast the coyote was moving when he hit the ground, as it clearly wasn't fast enough to cause any serious damage. Since energy can never be gained or lost, total energy at the top of his fall will be equal to total energy at the bottom of his fall. Therefore, initial kinetic energy plus initial potential energy is equal to the final kinetic energy plus the final potential energy. Since he is at rest before he begins to fall, the coyote's initial kinetic energy will be 0, and since we are trying to find his velocity when he hits the ground, his final potential energy will be 0. Therefore, the equation can be rewritten as initial gravitational potential energy is equal to final kinetic energy. We know that potential energy is equal to mass times acceleration due to gravity times the height, and kinetic energy is equal to 0.5 times mass times velocity squared. We can now plug these back into the original equation, giving us mass times acceleration due to gravity times height is equal to 0.5 times mass times velocity squared. After cancelling out mass and isolating for v, we get the equation v is equal to root 2 times acceleration due to gravity times the height. We know that acceleration due to gravity is 9.8 meters per second squared, and we determined that the height was 16 meters. We can now sub in our known variables and solve for velocity. After doing this, we get an answer of 18 meters per second, which will be his final speed when he hits the ground. That means that the impact experienced by the Coyote when he hits the ground would be equivalent to hitting a wall when driving at around 65 kilometers an hour. Thinking of it this way, it is hard to imagine that the Coyote could have been perfectly fine after this fall. Therefore, this is one example of bad physics within this cartoon. Our final problem will be a bit more complicated, as it will be a crash and chase problem. In this clip, Coyote is looking through binoculars when he spots the Roadrunner. He then grabs his fork and knife and begins his pursuit, eventually catching up to him. In the clip, it appears as though the Coyote ran a long way to catch the Roadrunner. However, we will be trying to determine exactly how far that distance was in meters. Assuming the Coyote started running right as the Roadrunner passed him, we can do fairly simple calculations to find their displacement. For this question, we only have two givens. We know that the acceleration of an average Coyote is 14.3 meters per second squared, and that the velocity of the Roadrunner, since it's constant, is always 8.9 meters per second. For this question, we're going to need two equations. The first will be for Wile Coyote, and will be delta d is equal to initial velocity times delta t plus 0.5 times his acceleration times delta t squared. The second equation will be for the Roadrunner, and will be velocity is equal to displacement over time. We can use this simpler equation for the Roadrunner because he is not accelerating and his velocity will remain constant. The first step towards solving this problem will be to rearrange both equations and isolate for delta t, because we do not know its value and will need to eventually cancel it out. The first equation for Wile Coyote can be simplified by crossing out initial velocity times delta t from the equation, because the initial velocity will be 0 and therefore that part will equal to 0. We can then rearrange the rest of the equation and isolate for delta t. Our final equation will be delta t is equal to the root of delta d over 0.5 times acceleration. Our equation for the Roadrunner will be far easier to simplify, as we can simply switch velocity and delta t, giving us an equation of delta t is equal to delta d over velocity. We know that in both equations delta t will be the same, as they both started running at the same time. Therefore, we can set both equations for delta t equal to each other, giving us a final equation of delta d over velocity of the Roadrunner is equal to the root of delta d over 0.5 times the acceleration of Wile Coyote. Squaring both sides of this equation will give us delta d squared over the velocity of the Roadrunner squared is equal to delta d over 0.5 times the acceleration of Wile Coyote. We can then cross multiply, giving us 0.5 times acceleration times delta d squared is equal to the velocity of the Roadrunner squared times delta d. Now, if we divide both sides by delta d, we are left with an equation of 0.5 times acceleration times delta d is equal to the velocity of the Roadrunner squared. Rearranged, this gives us delta d is equal to the velocity of the Roadrunner squared over 0.5 times acceleration of the Coyote. Finally, we can plug in our known values, giving us an answer of 11 meters. This means that according to physics, the Coyote and the Roadrunner both only ran 11 meters before the Coyote caught him, which is not what it looks like in the video. Therefore, we will say that this is another example of bad physics within this cartoon. Overall, the physics in Wile Coyote and the Roadrunner are not very good. If this were to take place in the real world, a lot of things would need to change to make it actually possible. However, since it's just a cartoon, they can get away with it. Thank you for tuning in to this episode of Physics with Graeme. See you next time.